All right, everyone. Thanks for coming today. We're really excited to kick back off with a very interesting talk on conformal geometry from entanglement by Xiang Li from UCSD. So, whenever you're ready, take it away. We're excited to hear about this.
Yeah, thanks for the invitation. Today I'm going to talk about the conformal geometry from entanglement. This is based on our recent work in arXiv. And this work is in collaboration with Isaac Kim, David Lin, and John McGreevy and Bowen. Okay, we can get started. So first I wish to give a one-sentence summary of the result. So consider there's a 2+1D gapped quantum system, many-body system on a disk like this, and they might locally interacting with each other. And we know at a low energy limit, it's possible that the edge can have CFT emerge. And we wish to ask the question, is the emergence of conformal symmetry related to quantum entanglement property in the system? So our paper gave a partial answer to this question. Indeed, there is some relations. And to summarize the result, we derive such a statement that for a quantum many-body state, for a quantum many-body state on a disk, here by disk, I mean a topological disk, if the state satisfies a certain set of local entanglement conditions, then one can define a notion of conformal geometry on the edge. So there are some phrases that I didn't explain here. So the first phrase is quantum many-body state. So which quantum many-body state should we study? And secondly, the phrase a certain set of local entanglement conditions. What are those? And also there's a conformal geometry. So by conformal geometry, I mean a matrix of the edge that encodes a global conformal symmetry. And why can we define the conformal geometry, and how is the matrix defined? So these are the main questions that I wish to answer in this talk. Oops.
Can I ask a question already just on the first slide? Maybe you're going to explain this, but is there a reason why we would expect the emergence of conformal symmetry to come from quantum entanglement? Like why would you postulate this before the project?
Yeah, so so first we know that entanglement, this emergence of conformal geometry actually is pretty robust, meaning if we consider a chiral gap system in the bulk, then the edge has to have some conformal symmetry. And then from the bulk, we know that there are some reason that the bulk has that robust property. This is based on the entanglement property, the previous work by Bowen. So if we expect such type of bulk edge correspondence, then if the bulk has that origin of robustness, then the edge might also have such an origin of CFT. This is one answer. The second answer is actually in a recent paper by David and John, they already discovered a way to seeing the conformal symmetry from the entanglement of the CFT ground state. So now we wish to generalize this to the gapless edge, and yeah, we can ask the similar question whether the CFT can emerge from the local entanglement property of the system.
Okay.
Sorry, my pointer seems issue. Yeah. Okay. Before going into the detail of the work, I'm going to talk about the physical background, the physical context, and the entanglement bootstrap. So the general background is quantum physics matter. We wish to apply the entanglement bootstrap to quantum physics matter. And what does this word means? So vaguely speaking, a phase of matter refers to a set of many-body systems that share the same or similar properties among each other. And these properties are usually called universal properties. Or specifically, a phase of matter can be thought of as an RG equivalent class. And all the systems in the same phase flow to the same RG phase point at low energy limit. Or in other words, at a large length scale limit. And the ground state of the system in the phase can be thought of as a representative state of the phase. So I will use this word representative state many times in this talk. So it just means the ground state of the system in the phase. And at low energy, universal properties of the phase emerge. So a famous example is for 2+1D gapped quantum many-body systems, anion can emerge at low energy. And the theory of anion can be described by topological quantum field theory, TQFT. So the general setting, the general physical context of this work is to study universal properties of a quantum phase of matter. Now I wish to talk about what is entanglement bootstrap, what it is about. So entanglement bootstrap can be summarized into this figure. It's mainly about how to derive universal properties of the phase from quantum entanglement properties of local regions on a representative state in the phase. So yeah, whether we can see such, say, anion types, the fusion from or the breeding from the local entanglement property, say this local regions, how to see such universal properties. And such a philosophy is also applied to phase boundaries, such as critical theories. So here are two examples. The first example is given a 2+1D reference state, anion data, such as anion types, quantum dimensions, fusion rules, can be derived from a certain set of conditions of entanglement entropies of local regions on the state. This example is for the phase. And there's also an example for the critical theory, this 1+1D safety ground state. So one can also construct the generators of the conformal group from the entanglement of 1+1D safety ground state. So in that sense, we can see actually the CFT, the conformal symmetry is already encoded in the local entanglement property of the CFT ground state. Before I talk about the detail of this work, I think I should introduce some quantum information preliminaries. This is because our entanglement bootstrap is to study entanglement, and the important tool for entanglement is to study entanglement is quantum information. So when we consider a system, we usually mean a quantum many-body system that consists many local degree of freedoms. And these local degree of freedoms living on many sites. And on each site, there's a local Hilbert space. And the total Hilbert space is just the tensor product of the local Hilbert space. And for a region, which is a collection of sites, there's a local Hilbert space associated with the region HX. It's just the tensor product of the local Hilbert space for the sites in the region. And the reference state is defined in such a tensor product Hilbert space. And to talk about the local entanglement property, we usually consider this quantity called local reduced density matrix and associated with the region X. And sometimes I will just call this local state. And it's defined as the partial trace of the global state. So taking this global state side, you trace out the complement of this X. Then you get the reduced density matrix of the region X. And once we have this reduced density matrix, then we can compute many important quantities. One of them is entanglement entropy of a region. It defined as this minus trace rho log rho. And sometimes if the state is clear, then I will just drop this psi, just write it as rho x. And with this reduced density matrix, we can also define the modulo Hamiltonian. It is just the minus log rho. And these two quantities will be used all the time in this talk. It's very important for our framework. Now, with this quantities defined, I can summarize the central question in entangled bootstrap in the following sentence. It's really about how to see or deriving extracting the universal properties of the phase from the properties of this set of reduced density matrix from a representative state. Okay. Now, for this work, we are focused on a particular universal property that is the gapless edge of chiral gapped systems. So we know in lots of 2+1D quantum many-body gapped systems on a disk, at low energy, the edge is described by CFT. So a famous example is quantum Hall systems. At low energy, they are described by Chen-Simons theory. And we know the edge of Chen-Simons theory is described by Weston-Wheaton CFTs. Now the question is why, how does such a CFT emerge, and whether such a CFT is related to the entanglement property of the state. And in this talk, I will particularly focus on the chiral systems. Our framework actually also apply for non-chiral systems, but with some change of assumption, but it also apply there. But for this talk, for simplicity, I will talk about the chiral systems. Okay. The main motivation of this work can be summarized into this question. Can edge conformal symmetry originate from a set of local entanglement properties of a representative state in a 2+1D chiral gap phase? People have already studied the origin of arXiv with different frameworks, for example, by assuming the bulk TQFT. And in our work, we wish to understand the origin from the local entanglement properties. And for this purpose, first, we must forego the CFT assumption in the framework. The edge CFT should be the logical consequence rather than a logical starting point. And then more specifically, the logical starting point should be some locally checkable conditions on the reduced density matrix for a given state. And it's a non-trivial task to identify such conditions. We hope to prove the existence of the edge conformal symmetry from these locally checkable conditions. And in this work, we made progress in answering this question. So specifically, we proved that there is a notional matrix that encodes global conformal symmetry, conformal geometry for short, can emerge from from 3 locally checkable conditions on a given state. Okay, before I dive into the detail of this work, is there any questions?
I mean, so just to confirm,
Mhm.
the point you're trying to make is that, I mean, if I had a TQFT like Chern-Simons theory or something like that in the bulk, then there's the usual story that tells me that there's the chiral boundary conditions have some conformal symmetry or something like that. But you're saying instead, you're working with some concrete lattice model, and you want to essentially prove that there's like a conformal geometry that arises from that perspective instead.
Yeah.
Okay, great.
Yeah, but we also hope that we can generalize our framework to continuum field theory. But at this moment, the setup is on lattice model, like tensor product hyperspace.
Mm.
Okay, now I'm going to talk about the detail of the work in emergence of conformal geometry. So first, here's an overview of the framework. So the starting point is 3 assumptions on the quantum state. The 3 assumptions are bulk A1, non-zero chiral central charge, and the stationarity condition. I will explain each assumptions later. And from these 3 assumptions, we can derive the emergence of cross ratios. And from the cross ratios, we can further derive a notion of conformal geometry. Okay. So for the rest of this talk, I will first talk about the 3 assumptions, then talk about how does cross ratio emerge from these assumptions, and how can we derive the conformal geometry using the cross ratio.
May I ask a quick question? So, how does your chirality plays with the fact that so you want the chirality, and at the same point you want the finite dimensional Hilbert spaces at each lattice site. Like, what example do you have in mind?
Yeah, it's a good, very, very good question. Indeed, we know that once we have the non-zero chiral central charge in the usual sense, then there shouldn't be a finite dimensional local Hilbert space. So to answer this question, I would say there are 2 ways. One is we actually don't require the local Hilbert space to be finite dimensional. This is the first answer. The second answer is we can also ask the following question. We can assume the axioms, like we can assume the finite local Hilbert space, and in that case, the axiom won't be exactly satisfied. Like the correlation length cannot be exactly 0. So and also the chiral central charge is not exactly defined in the same way as the field theory. It's computed from this modular commutator. And actually, it doesn't exactly compute the chiral central charge with some error.
So, what about like 0 for the chiral central charge? Is it obvious that you will get a CFT or?
Yeah, for yeah, the answer is yes. For zero central charge, we can also get CFT, but the assumptions are a little bit different. So to summarize the new assumption, so to study non-chiral state, we remove this second assumption, and add another one, which basically is saying that on the edge, the entanglement spectrum is not flat. And from there, we can also derive the emergence of cross ratios. We can also see the conformal geometry. So the non-zero chiral central charge is not that crucial. It's just because the simplicity, like I can present a coherent story. But for non-chiral state, the story is a little bit different. But we can also see this conformal geometry.
Yeah, another small comment I'd like to add is that there is a better studied case that's the gap, the boundary. That is certainly a special case of conformal boundary, but it's a trivial case. It's central charge equal to 0, so it's a But yeah,
but there'll be like sort of no geometry probably.
Right, this work is more interesting because it also tells us what the boundary behaves for non-zero central charge.
Well, right, but yeah, I'm just like you make it seem like even non-chiral CFT like already obvious, I guess. Yeah, it's not. I would say it's not, but yeah, let's hear about it. Chiral CFTs anyway.
Okay.
Thank you.
Okay, so yeah, so in the rest of this talk, I will first talk about assumptions, the emergence of cross ratio, and the conformal geometry. So let's get started. The first assumption is bulk A1. The statement of bulk A1 is the following. For any D-select region in the bulk of linear size order 1, it's just one letter set, with a partition BCD that's topologically equivalent to this figure, this type of partition. So there's a center C and 2 buffers B and D, and BD totally buffer this C away from the rest of the state. And in this region, we define such a linear combination of entropies that are BCD. It is the buffer with the center BC and CD minus the 2 buffers B and D. What does this assumption really tell us about the state? So first, this assumption can be almost the same as saying the bulk is gapped. This is because for many gapped quantum states, the entanglement entropy satisfies area law, meaning for region A, the entanglement entropy has a leading order proportional to the circumference of the region and a subleading term, that is a topological entanglement entropy, a property of the phase, and also some extra terms that vanishes when the subsystem size goes to infinite. And so using this result of area law, we can actually see the A1 is satisfied. And secondly, bulk A1 implies a certain quantum Markov chains. So what I mean is consider such a BCD and consider A, which is any region outside BCD. And the bulk A1, this condition is satisfied, implies that this AC condition on B is a Markov, meaning the conditional mutual formation AC condition on B is 0. And this is equivalent to such a decomposition of modular Hamiltonians when act on the state. So KABC, which is the modular Hamiltonian of the reduced density matrix rho ABC, is equal to, can be decomposed into KAB plus KBC minus KB when act on the state. So in summary of this bulk A1, it really is saying that the bulk is gapped and the bulk has a certain Markov chain structure. The second assumption is non-zero chiral central charge. So we know that if you assume the edge is described by CFT, then the chiral central charge can be computed by CL minus CR, meaning that it characterizes the difference between the number of left movers and right movers along the edge. But this computation require an information of the edge CFT. What if we don't know the edge CFT? We just give you the quantum state and don't tell you what that is. Then chiral central charge can be computed by modular commutators. This is by this work, Bowen, Kim, and Cato. So from the bulk, we can use the modular Hamiltonian KAB, KBC, take the commutators and compute the expectation value, and we can see it actually equal to pi c minus over 3. So the second assumption is just the chiral central charge is non-zero, meaning it's a chiral state.
You mentioned earlier that there's some error in this formula when you have a non-zero correlation length.
Right.
Can you comment on what that error looks like?
Yeah, the error. So we numerically verify the error. It could be exponential decay with the system size. So as you zoom in, as you zoom out, as you increase the subsystem, it could be exponentially decay to the correct value. And also we observe it could be power law decay to the correct value. But in any case, it's a decay into the value. And I think.
So what was the power law case?
Yeah, the power law case actually is very confusing. It's in both cases, the power law and the exponential law are observed in P plus IP superconductor, non-trivial phase, the chiral phase. But with changing parameters, it's possible that it's power law or could be exponential law. That's a very confusing feature indeed.
Changing the parameters of the P plus IP phase.
Yes, yes.
So like adding interactions or something.
You don't need to add interaction. It's just the usual P plus IP Hamiltonian, but change the parameters. It's yeah, it's kind of confusing.
So do you understand this?
No, I don't really understand why it could be, because without it should be the same phase.
Yeah, by confusing, you just mean you want to understand better, right? It doesn't contradict with any principle.
Right, it doesn't contradict any principle, but I don't know why it behaves differently for different parameters.
I see. Interesting. Is that in your paper?
It's in one of the paper. There's also another paper by us. It's called Warsoro generators from a single wave function. In that paper, we discuss the exponential log case, and also we list the parameters that can give you the power law. And actually, the parameter is not a fine-tuned parameter. It's a range of parameters. That's kind of confusing.
I see. Okay, thanks.
Yeah, I also wish to comment that it's possible that this computation give you a wrong result. I learned this from Bowen, and I guess Bowen learned this from KTF, that they construct some.
I guess I learned from Michael Levin and
I see. Michael Levin. Okay.
Julia, I guess. They had some, you know about spurious topological entanglement. They had a similar model for spurious modular commutator. The model violated one of our assumptions, the bulk A1. It's kind of expected we can have such examples. Although the other claim is that if the A1 is satisfied, we believe this formula always give us the right answer.
Yeah, and it's also observed in the numeric that the error of this formula is correlated with the error of A1, even in the P plus IP case I described.
Do you remind me which one A1 is?
Sorry, yeah. A1 means this linear combination of entanglement is 0. So in real system, in real chiral systems like P plus IP, there is not exactly satisfied. There's some error. And the error is correlated with the error of this C minus. So P plus IP C minus should be a half, but yeah.
Is it like a constant shift error?
Finite size errors.
Yeah, finite size error. Yeah.
It's easy.
Can I ask, so you're saying you computed it numerically? So there is a P plus IP Hamiltonian and something else.
We put a P plus IP Hamiltonian on the square lattice. And P plus IP is a free fermion, so we can compute the system size to be very large. And then we can just compute these KAB, KBC commutators and
and something else.
There's nothing else. What do you mean by something else? Like what's something?
No, I'm just curious. Like you're saying you computed numerically. I just wonder what model.
That's just P plus IP, the P plus IP without any disorder, without interactions.
Thank you.
And in the original paper, we also did for some interacting models, like a wave function of semion represents a semion with up to 30 qubits or something.
Right, for semion, it's an interacting model, and we also, but for that case, because it's interacting, so we cannot really go to too large.
What did you use? Like Laughlin wave function or what?
Right, Laughlin wave function. Yes.
Essentially, it's a Laughlin wave function. It's a discrete version people can put on lattice. And
All right. Thanks.
Okay. These two bulk assumptions, bulk A1 and non-zero chiral central charge, are borrowed from previous work. So an intuitive understanding of these two assumptions is just saying that the bulk is gapped and chiral. And in this work, we identified a new condition called stationarity condition on the edge, and study whether the edge conformal symmetry can be derived if a given state satisfies this condition. To talk about this stationarity condition, I first need to define the two quantity C total and eta. So these two quantity are meant to take the role of total central charge and the cross ratios. But at this moment, we just define it from this linear combination of entanglement entropy, and we don't know whether they really behave as we expect. But later we can see under the assumptions we pose, indeed, they can interpret it as central charge and the cross ratio. Okay, so how does C total and how does eta is defined? So first we consider a local region near the edge. It's a disk, and with this partition A prime, B, C, C prime. It's similar to the A1, meaning it has a center B and two buffers A prime and C, C prime. And the A prime, C, C prime buffer B away from the bulk. And on this region, we call this conformal ruler. We define two quantity delta and I. Yeah, there are just these two particular linear combination of entanglement entrophies. I think it might be hard to actually memorize, and I don't think it's necessary to memorize it in order to understand the talk. I think the one feature I wish to point out is we define this way because it cancels the UV feature in the bulk. This is a very important thing. But for the actual definition, like what's the linear combination, that I don't think is necessary to memorize. Okay, so with these two delta and I defined, we can first define the C based on this equation. So by solving this equation, we compute the C total. And with this C total, we can compute this eta. So eta is just the first term here. So why we define them in this way? It has a CFT motivation. So consider a 1 plus 1 is CFT on a round disk. Round disk means the edge is just a circle, and the bulk is empty, just the product state. So there doesn't contribute to the entanglement entropy. So in this case, in this example, the delta has only contribution from the edge. So it is equal to SAB, SBC minus SA minus SC. And we know that for CFT grounded on a circle, the entanglement entropy of an interval of core distance L is equal to C total over 6 log L over epsilon, where epsilon is a cutoff, and the C total is a total central charge. So with this formula, we can explicitly compute this delta and I, and they are equal to minus C total over 6 log eta g and minus C total over 6 log 1 minus eta g. So eta g here is the geometric cross ratio on the circle. So defined as the core distance LA times LC divided by LAB and LBC. So once we compute these two quantities, we can plug them into the definition, and we can solve for C and eta. We can verify that indeed C is the total central charge of the CFT and eta is the geometric cross ratio. So here is a example we are assuming CFT, but in our case we wish to in our framework we wish to throw away the edge CFT assumption, and just formally define this C and eta this way and ask when they can be interpreted as a central charge and a cross ratio. Okay, here are two important properties of the C and eta. So the first is the existence of the solutions. So if delta and C are greater than 0, so that means the edge is not gapped, because for gapped edge, delta or I can be 0. If delta and I are greater than 0, then a solution for both C total and eta exists. And we can show C is greater than 0 and eta belong to 0 and 1. And another important property is C and eta are property of the edge, meaning it doesn't depend on the choice of the region inside the bulk. We can deform this conformal ruler, and the value of delta and I are invariant under any bulk deformation. Because delta I are invariant so C and eta also invariant. Yeah, so this is the most important feature of this definition of C and eta. This is why we define them this way, using the delta and I. Okay, with this C and eta defined, now I can talk about the stationarity condition. So the statement of the stationarity condition is under any norm preserving perturbation of the state, like psi goes to psi plus epsilon psi prime. On any conformal ruler, the resulting variation of C in linear order of epsilon, that is just the first order of the variation in terms of epsilon, vanishes. So delta C is 0 for any conformal ruler. So we can draw some picture like this. So for space of states, it could be a set of points, or it could be minimal or maximal extreme. So the stationary condition really is saying that we wish the state to be at a set of point or extremal in the space of state in terms of the C total. Before I talk about the intuition of why we put this stationary condition, first I want to talk about a vector free-point equation. So in 1 plus 1D safety ground state, there actually is a vector free-point equation derived in this paper. So the vector free-point equation is saying that there's a certain linear combination of modular Hamiltonians called delta hat. K delta and K delta eta act on the state is proportional to the state. And this K delta is defined as eta J delta hat plus 1 minus eta J I hat, where eta J there is the geometric cross ratio of interval ABC. And now we wish to generalize this to 2 plus 1D. So first, in 2 plus 1D, as I mentioned, we don't want to assume any symmetry, or we don't want to assume any distant measure on the edge. Therefore, we cannot really define eta G, the geometric cross ratio. Therefore, we replace the eta G with this eta D we define. And whether we can call this a cross ratio, that's that's something we need to verify. And for delta hat, we replace this delta hat with this one. The reason for doing this is because we wish that the delta hat has no action in the bulk when acting on a state, meaning it only creates edge excitations. And similarly for I hat, it also creates only edge excitations. And we can see, suppose the bulk is empty, then this definition reduced to this one. So this is the correct generalization of the 1 plus 1D case. Now we can ask the question, could there also be a vector free-point equation for 2 plus 1D edge? Meaning whether there could be a KD eta acting on the state proportional to the state. As it turns out, the answer is yes, if you assume the stationarity condition. And moreover, it's actually equivalent to a stationarity condition. So there's a theorem we proved in the paper saying that for any conformal ruler, if the C is stationary, then if and only if there's a vector free-point equation associated with a conformal ruler. I think for the time limit, so I will skip the proof. I will just point out the most important feature of this vector free-point equation, that is, it turns this stationarity condition to a locally checkable conditional state. You know, the stationarity condition is pretty hard to check straightforwardly because you need to vary the state arbitrarily and verify whether it's really stationary. With the vector free-point equation, we can simply check this in the following way. So first we compute the eta, and then we just check whether this KD acts on the state proportional to the state. So therefore, the stationarity condition can be locally checked by the vector frequent equation. And why do we assume the stationarity condition or vector frequent equation? So first of all, it indeed captures the desired state we wish to study. We know that if the edge is described as CFT ground state, then the stationarity condition of the vector frequent equation is satisfied. So in 1+1D, it's proved in this work, and for 2+1D chiral edge, we also have some argument in this work, and also have some numerical support. One motivation of turning this condition into an assumption is a speculation that the C total could satisfy a C theorem. One statement in the C theorem is the stationarity. The C function should be stationary against any perturbation of the Lagrangian, the Hamiltonian, and when the system is at RG critical phase point. In summary, the assumption isn't so strong that it rules out the interesting system we should study, and also is very powerful, so that we can derive some non-trivial statements of edge phases of the system. And now I will discuss what are those non-trivial statements. I think I should pause for questions. Any questions so far?
Oh, actually, I have a small question. I thought it might be useful to give some more background. 2 pages ago, so you first started from talking about 2D, so one dimension, and you said there is a geometrical cross ratio usually, and for 2+1D, why are we talking about no distance? Suppose I have a really round cylinder with a boundary, very round boundary. Can I just use the geometrical cross ratio there?
Right. You can naively use the geometrical cross ratio there. However, whether the system has the transition symmetry is you need to check the Hamiltonian. So if you put the system on a cylinder, but you put some disorder to break the transition symmetry of the Hamiltonian, then you shouldn't use the geometric cross ratio.
And do we still expect a cross ratio and CFT still make sense there?
Yes. Once suppose we verify our assumption is satisfied, then yes.
And why this is special to 2D? For example, I can try to do the same thing for 1D.
You can also do you can also do the same thing for 1D.
Yeah. And the conformal symmetry is still there?
If the assumption is satisfied, then yes.
Does it satisfy? Like, what is there different? Like, we can do the same thing for 1D and 2D. So why we start
the difference of 1D and 2D is really not important. There really isn't any difference between 2D and 1D. It's just because for 1D we can simply treat as a 2D with empty bulk.
Yeah. Okay.
And another comment is there is some difference. One important difference is for 2D sometimes the edge can be pretty robust, but for 1D is not the case. For 1+1D CFT, we can gap out the edge by some relevant perturbation. However, for 2+1D edge, in some case, for chiral case, it is the case. For non-chiral case, if the bulk has non-zero higher central charge, then the edge is also ungappable. So you cannot really add some local perturbation to gap out the edge. So in that case, we expect the stationarity condition, the assumption is more robust for 2+1D edge.
So you are saying for 2+1D, sometimes it is even more robust in the sense that the minimal total central charge of the edge may not be 0. Maybe you are already in a gapless edge which reaches the minimal central charge, so you can never make it smaller. And perhaps the conformal symmetry is even more robust there.
So in that case, will correspond to this case, like it's a minimum but non-zero minimum.
And I guess it's very easy to make models with like non-uniform, like adding disorder, as you say. So the geometrical cross ratio doesn't make sense there, but somehow maybe the conformal symmetry does emerge. Good.
Okay, any other questions? Okay, yeah, so far we talk about the three assumptions. The bulky one, this linear condition of each of Fibonacci's, and the non-zero Cartesian charge, and the stationarity condition, or equivalently using the vector frequency equation. And for the rest of the talk, I will talk about the eta we defined. It could be interpreted as a cross ratios. And also from there, we can see the emergence of conformal geometry. So to first talk about eta as an emergent cross ratio, there's a very useful proposition we prove in the paper. That is, we can also compute the eta using edge modulo commutator. So the proposition is the following. If the state satisfies the three assumptions, then for any conformal ruler, the modulo commutator JABC defined this way is equal to minus pi c minus over 3 times the this eta we defined previously using the delta and I. So this result gives us an alternative way to compute this eta. And with this result, we can derive a consistency relations of cross ratios. So we know actually the cross ratio, in fact, satisfy a bunch of consistency relations. So using the edge modulo commutator, we actually derive that the following relations. So consider such a region ABCD XYZ. It actually have 5 conformal rulers. So we can talk about the cross ratio of interval ABC or BCD, or we can group AB together and consider conformal and consider the cross ratio AB, C, and D, AB, CD, and A, B, C, D. And in fact, we can derive that the cross ratios on the larger intervals, say this one, A, B, C, D, can be computed from the cross ratio on the smaller ones, B, C, D, and ABC this way. And similarly for A, B, C, D, and A, B, C, D, they are all decided by the cross ratio on the smaller intervals. Yeah, here is how it's derived. So I think for the time, I will skip the derivation. Yeah, the main technique I'm using is using the vector frequency equation and also using the edge modulo commutator result. So we can get a bunch of equations, and by solving the equations, we can derive these relations. Yeah, I will skip this derivation. So with such a relation derived, why we can see is this eta is really a cross ratio. This is because using this cross ratio, we can construct a map from the edge of the state to a bunch of points on the circle. So we can map the point on the edge to a bunch of points on the circle. And also the map makes sure that the cross ratio, the quantum cross ratio, is equal to the geometric cross ratio computed from the circle. And also, by constructing the map, these points are following the same orientation as the point on the edge. And also a bonus result is this relation also implies the C total actually is the same for different regions along the edge. This is a bonus result, but since this talk is mainly about the conformal geometry, so I will focus on the cross-ratio stuff. And this map is very important. It'd be very useful for us to study conformal transformations. So what does it mean? So using this map, we can obtain a distance measure or a matrix of the chiral edge. We can simply assign the distance using this distance on the circle. And then we know the physical observables should depend on the cross ratios. So this map can actually give a decent measure for this observable. And also because this map is constructed using it's constructed such that the cross ratios are matched with each other. It actually encodes a certain global conformal symmetry, PSL2R. So recall, cross ratio are invariant under such a transformation. Therefore, two constructions of the matrix, meaning the construction of the map, are equivalent to each other if they are related by a SL2R transformation. And they are both valid matrix of the chiral edge of the quantum state. So in that sense, we can see the matrix, in fact, has a certain global conformal symmetry encoded. And moreover, we can use it to talk about not global conformal, but Varsoro, but defects one. So consider on the original state, we have the assumption satisfied. Then we can construct this map to put a point on the circle. And suppose under some unitary, we get a new state, psi t, and this psi t also satisfies assumptions. Then we can also do the same construction, but map the point to a different position on the circle. So by comparing these two, we can actually get a map from a point on the circle to a point on the circle. In other words, we get a defects one. And then because the map has a PSL2R symmetry, so this map is modeled out by this PSL2R. In fact, such a unitary can be realized by modular flow. And we also observed that indeed under this modular flow just means some unitary flow generated by the modular Hamiltonian. And we observed that for this modular flow, the three assumptions in the bulk is still satisfied. And indeed, we can define the quantum cross ratio for the new state. Therefore, we can find a corresponding geometrical motion or defects one, in other words, of the points on a circle by constructing this map. So yeah, using this way, we can really talk about the conformal transformation of the edge. And we can map it to the circle and talk about the actual defects one on the circle.
So question here. So you said the modular flow, so here is U some unitary evolved state. After that, the edge still have a set of cross ratios if the original state has a cross ratios. This works for a generic one-dimensional chain, or is for state with only left mover, no right movers?
Right. In this case, it's only for the chiral, purely chiral state, I should say, because
purely chiral means
the edge only has one mover. Yeah, only has one.
Only has left mover, you mean?
Yeah, one mover. Yeah. And yeah, the reason is because if there are two movers, then they transform differently. Therefore, you cannot. Therefore, it's more like a two copy of the points. And once you flow them, they flow differently. So the point like a split. So therefore, it's kind of tricky to talk about such a map in that case.
But it's okay to have two left movers.
If the two left movers are, have the same velocity, I would say yes. If the two movers have different velocity, under the modular flow, they flow really different. Like the 2 points split into two, 1 point split into 2 points, then still not okay.
Okay. Okay, I guess we don't know such example. Well, under modulo flow, my impression was they all flow the same way. Yeah, that's it. And something we can talk about later.
Okay. Yeah, basically that's the end of the story. So now I'm going to discuss some open questions. There are actually many open questions. I just select some of them. So the first question is, what's the lower bound of C total, and whether it's related to ungapability? So there's a conjecture that if the stationary point of C is a local minimum, like this, and a non-zero at the minimum point, then the edge should be ungapable. And also the minimum value is expected to be the total signal charge of the arXiv. So to study this, we actually need to study the C away from the phase point. So one case is, how does it behave under the arXiv flow? So people have defined this C function for 1 + 1 relativity QFT. But in our case, we define it in a more general setting. We don't require any symmetry. We just define it in terms of quantum information properties, quantum information quantities. So the first question is, does it monotonically decrease under arXiv flow? And also, can we obtain the information of the relevant operators by studying the Hessian matrix of the C total? So finally, I wish to just mention a very ambitious picture, that is whether we can get a landscape of phase matter by this C. So it's something like this. We suppose we draw the C in a space of states, gapless state, whether the critical point, whether the saddle point corresponds to some safety phase point, and if it's like a minimal like this, then it's ungapable, and or maybe like this, it's also ungapable, but for non-chiral edge. But for gapped edge, it should just be 0. We can prove if it is 0 in that case. Okay, yeah, with that, I will end the talk. Thanks for your attention. Any questions?
Thank you. Thanks for the talk. Great
So can you
pictures.
get yeah, sorry.
Mm-hmm.
Can you get like more like fine data, like the spectrum of our CFT, like spectrum of prime operators, fusion rules, and so on?
Sorry, I didn't get the question.
Can you get the spectrum of prime operators, fusion rules?
Yeah, we I think one of the collaborator, David, verified that in 1 + 1 CFT using some qubit to build up the critical model, and by studying the spectrum of the C, and indeed the Hessian, the negative value, the negative eigenvalue of the Hessian correspond to the relevant operator of the set.
Also, as I see it, you guys getting something like a conformal net, or approximation of a conformal net. So there must be a way. So it's a theorem that you can get the whole like representation of your way from a conformal net, but it's kind of tricky. But you should be able to get everything.
You mean by doing the conformal map on the state, and you can read off the spectrum of the relevant operator, or the conformal dimension?
No, I'm just. I guess it's just a comment that I think that what you're doing in general, like this covariance with respect to the conformal transformation stuff. This is, I mean, like you basically are obtaining some properties of a conformal net, and this is like an abstract object. Like you associate observables to a region, and if its region is included in another region that's included in observables and stuff, and then like these observables must be transformed covariantly with the with the conformal transformations. And in principle, it is a theorem that this data suffices to define the like CFT, the standard CFT data, like representation of a VOA stuff. Yeah, it's a kind of long way anyway.
And I'd like also make some remark on what people have done. So in terms of primary, indeed, one thing Xiang mentioned was the previous work by David and John. They find, for example, they can use the quantum state to reconstruct the Hamiltonian, and they find the low-lying spectrum that match the CFT spectrum for models like Ising and so on. And well, what progress we may hope to achieve comparing to that if we pursue this research program. One thing is that phenomenologically sometimes one thing works, but we would like to know under what condition we are sure that a procedure works, and that's a mystery at the moment. So what we're trying to do at the moment is to identify the conditions on the state. So we will try to say if the state satisfies those conditions, some procedure of considering primary and so on, it must work out. Yeah, that's what we hope to do, and that's the ongoing work.
Yeah, I think in summary of what Bowen said, it just we wish to throw out the safety assumption. Instead, we assume some locally conditional state, and we wish to see the safety feature using this condition instead of assuming safety in the first place.
Maybe I could ask a question then on that theme. It seemed like your assumption one, so it basically says that if a thing satisfies assumption one, it's a quantum Markov state, right?
For some region, it's a Markov chain, yes.
For some reason, region.
Yeah, for some region.
I see, specifically of that geometry. Okay.
Yeah, like I think the crucial thing is A and C doesn't touch each other, and then C is buffered by some region. Then the A and C and the buffer is a Markov chain.
Are states that satisfy this quantum Markov chain property, are they like not? So I know very little quantum information, so please excuse my ignorance. But like, for example, I know that in continuum quantum field theory, for example, I think it is hard to get a state that satisfies the Markov property. Like I think they're rare by Ricci-Schlieder theorem or something.
Right, because of the Ricci-Schlieder theorem, it's basically impossible to get a Markov state because the Markov state actually imply A and C is a separable state. Rho AC is a separable state.
Yes.
Meaning there are no quantum information, equal entanglement, but Ricci-Schlieder theorem said there should be. So in that sense, it shouldn't have the relativistic quantum field theory shouldn't satisfy this. And the
separable, by separable you mean split state? What's separable?
Oh, by separable I mean intuitively it's a sum over bunch of product state. I mean it's a convex combination of bunch of product state between A and C. So that's just some classical correlation and no quantum entanglement. And so for relativistic CFT, I think just one special example. For 1 + 1 is CFT, if some region on the lag cone and some region in that case, there is a Markov. But for other cases, I don't think there is.
Yeah, I know that you have to be on some sort of null surface or something to get this in continuum. But okay, but not in the continuum. Then, in principle, these things are not super rare. Is that the idea?
Right. It's very common especially for the topological order phase. For example, say the quantum double model satisfy this, and the stabilizer model, or actually it's pretty common in the 2 + 1D gapped states.
I see. Okay, thanks.
Yeah, and by the way, we can I'd like to mention two related puzzles about quantum Markov chain. Quantum Markov chain is kind of pretty well understood in some way for people in study quantum information, but there are two variations of the problem is currently hard. One is a quantum Markov chain, infinite dimensional Hilbert space. There's no the structure theorem people proved apply only for finite dimension, so that's one open problem. And another problem. Open problem is approximate quantum Markov chain. Even in finite dimensional Hilbert space, they don't have such powerful theorems yet. Sometimes we'd like to use some theorem we find they haven't proved yet. It's quite exciting.
Yeah, one comment to both the comment, two comment maybe. So the first is for the structure theorem. There is a proof, but you assume the entropy is finite. But
you mean a proof in infinite dimensional Hilbert space?
Infinite dimensional, but they don't. But with the finite entanglement entropy, but the Hilbert space can be infinite. They are also a structure theorem. And I think the tricky case is, for a certain type of von Neumann algebra, the entanglement entropy actually diverge. And whether we can talk about the structure theorem in that case, that's the tricky thing. And for the second part, I think there are some for the approximate quantum Markov, I would say there are some different ways to define this word. If you just define it in terms of conditional mutual information, then we know such an example that the conditional mutual information can be pretty small, but it's really not like a Markov state.
That happens for infinite dimension, right? It's a sequence with the Hilbert space dimension become larger and larger. That what you said is more and more true.
So I would say we can ask what we really need. That is the, say this decomposition is what we really need. And then maybe structure theorem or maybe recovery, that's what we really need. But yeah, we can, ask the more specific question, like suppose this is approximately satisfied, then what's going on, something.
See, thank you.
Thank you.
Are there any other questions from anyone else? Okay, I'm hearing and seeing none so far. So with that, let's thank the speaker again. It was a nice talk.
Yeah, thanks for the
Thank you.
invitation. Thanks for the questions. Thanks for having
it's
me.
very good. Thank you.
Thanks.